Look at this. This is the Spintronics game. How cool is this? Now, they did sponsor the video, but I personally bought this second kit as I liked it so much. And here's why. This is a transistor. There's also a capacitor, an inductor, a resistor, a switch, an ammeter, junctions, etc. It's all powered by a mechanical battery. We use a chain to transfer the battery's energy to the components and make mechanical versions of electrical circuits. The energy transfers from the battery to the component and then back to the battery, just like an electrical circuit. I'm going to show you how to use them all, and there's even an online simulator. I'll leave a link for you in the video description. Do check this out. Electricity is hard to visualize because we can't see electrons in the wire, but we can see how a chain moves. We can add a blue link to make it even easier. We can also see and feel the voltage of the circuit, but I'll show you that part later on in the video. Notice that if I use this 1000 ohm resistor, the chain turns slowly. But if I use this 200 ohm resistor, the chain can move much faster because the resistance is lower. Just like a larger current flows in a lower resistance electrical circuit. The speed of the chain represents the current. If we remove the resistor, we get a short circuit. All the energy has returned to the battery without any resistance. In electronics, we can view the current with an ammeter, but that won't work with chains. So instead, we use this device, which lets us hear the current. The lower the resistance, the higher the current, and so the higher the pitch and volume will be. A low current circuit will produce a low pitch. But don't worry, there's a whole puzzle book with these kits, which explains the components, provides tutorials, and sets you challenges. Now, the answers are in the back, but don't cheat. There's also a beautifully illustrated storyline for you to follow, teaching you about electrical symbols, how circuits work, and also giving you equivalent circuit diagrams. This simple series circuit has a battery, a switch, and a resistor. The switch lets us control the current. So if we connect the mechanical battery to the switch, then the switch to the resistor, we can control the chain using the switch. We could make the same circuit with just one chain also. The wire must come back to the battery to complete the circuit, and the chain must also complete the circuit to work. In a series circuit, the current is the same anywhere in the circuit, and the chain is the same speed through all the components. If we add more resistance, the current reduces, and likewise we see that the chain moves much slower. What about this parallel resistor circuit? How could we make that? Well, notice there is a junction in the circuit which divides the current. Well, we have a mechanical junction too. So if we connect the battery to the junction, and then we connect the first resistor and then the second, we now have a parallel circuit. Notice the chains are not the same speed. It's slower on the high resistance circuit, just like less electrons flow in the electrical version. Parallel circuits divide the current. If we added a resistor here, we would make this a parallel series circuit. The power must flow from the battery to the junction, then through either of the parallel resistors, and then through the series resistor to get back to the battery. Same as if we had an electrical circuit. What about a capacitor? If we connect a battery to a capacitor, it instantly charges to the battery's voltage. Then it stops because there's nowhere for the electrons to flow to. Same happens when we connect the mechanical capacitor to the battery. The battery stops charging it, and we have stored energy in the capacitor. In this case, the energy is stored within this spring. Notice on top it shows 6 spin volts, and that's because the battery is also rated for 6 spin volts. We have to short the circuit to discharge the capacitor. We can slow the charging rate down with a resistor, because the resistor limits the current. Same with the mechanical capacitor. It charges slower with the resistor connected. We could add a switch to control when the charging occurs. We just add a switch in series. To discharge the capacitor, we need another path with a switch. By opening the first switch and closing the second switch, the capacitor can discharge. Same with the mechanical circuit, but the capacitor discharges instantly. How can we stop that? Well, we can add another resistor, and that slows the discharge rate down also. You might know that when we place two equal size resistors in series, we create a voltage divider. The voltage drop across both is equal, and so if we measure the voltage between them and ground, we see half the voltage of the battery. So if we had two 500 ohm resistors in series, how could we measure the voltage? Well, we place a junction between them and then connect the capacitor to the junction. And now we see that the voltage is 3 spin volts. But if we swapped resistor 2 for a 1000 ohm resistor, the voltage increases to 4 volts. If we instead swapped resistor 1 for a 1000 ohm resistor, then we read 2 spin volts. The total always adds to the battery's voltage. So if this resistor is losing 2 volts, then the other must be losing 4 volts, and that would make the 6 volts of the battery. This is Kirchhoff's law. The sum of all the voltages is 0. The battery provides 6 volts, this resistor subtracts 2 volts, and this one subtracts 4 volts, giving us a total of 0 volts. Now, if we place 3 resistors in series, sharing one chain, how can we measure the voltage drop of each resistor? We just swap the resistor for a junction. Connect the resistor to the junction, then connect the capacitor to the junction also. The resistors are all in series still. The junction sends power to the resistor and then back to the other resistors. The capacitor does exactly the same, so it's in parallel with the resistor. The battery provides 6 volts. The first resistor loses around 0.7 volts, so the chain here has around 5.3 volts. Then the second resistor loses around 1.8 volts. So the chain here is 3.5 volts. And the final resistor loses 3.5 volts. So the chain here is 0 volts. The total sum of the circuit voltage is 0. The larger the resistor, the larger the voltage drop. Remember, voltage is a pushing force in a circuit. We often think of it like pressure. So on the first 200 ohm resistor, if we remove the capacitor and hold the top cog with our fingers, we can feel a small pushing force. But if we try it with the 1000 ohm resistor, the force is much stronger because the voltage drop is much larger. So we can feel the voltage in the circuit pushing against our finger. And we can see the current represented by the speed of the chain. We also have this component, the transistor. A transistor is used to control other circuits. Here, the LED is off. The transistor is blocking the current by providing a large resistance. But when we apply a voltage to the control pin, the resistance reduces and allows current to flow, and so the LED turns on. The more voltage we apply to the control pin, the lower the resistance will be. With the mechanical transistor, the top cog is the controller. The lower cog is the circuit we want to control. Instead of an LED, we will use a resistor. Notice it doesn't rotate until we apply a voltage or pressure to the top cog. The further we turn it, the faster it spins. That's because the lower cog is connected to this rubber ring, and these little arms are pushing against it, applying resistance like a brake pad. But if we turn the top cog, the arms are pulled inwards, which lifts them off, and so the resistance reduces. So how do we control the top cog? Well, we could use a switch, but as soon as we apply voltage, it fully opens and then we can't turn it off. It's just stuck open. So we need to connect a resistor in parallel so that when we turn the switch off, the transistor can discharge through the resistor. For the control circuit, we will use a resistor and the speaker. But when we press the switch, it doesn't turn on. That's because we need a power supply to this section. So we add a junction, then connect the resistor to the junction and also the switch. Now when we press the switch, the transistor opens, allowing current to flow through the speaker. We also have this component, the inductor. You can see that it stores rotational energy, and in Spintronics, that is current, whereas a capacitor stores pressure, which is voltage. If we connect the inductor and the switch in series, when I close the switch, the inductor turns. It takes a moment to charge and get up to speed though, but when I open the switch, the inductor destroys the circuit. And that's because it has to release the stored energy and it now has nowhere to go, so it forces its way out. We have to add a resistor in parallel with the inductor. That way it has a path to dissipate its energy. Notice that both the resistor and the inductor rotate at the same time in the same direction. The inductor takes longer to reach its top speed while it stores energy. The resistor is almost instantly at top speed. But when I open the switch, the resistor reverses direction. Do you see how the chain reverses direction? In the electrical circuit, we can see that when I power the circuit, the current flows through both components. It slowly increases through the inductor while it stores energy in its magnetic field. But when I open the switch, the magnetic field begins to collapse, and this pushes the electrons. They now flow through the resistor in the opposite way, and that's so they can get back to the inductor to keep the current moving, just like we see the chain reverses in the mechanical circuit. Now, a diode is a device that only allows current to flow in one direction, but it requires a small voltage to open and allow current to flow. We can make a diode from the transistor by connecting it like this to a connector. When I apply a small force or voltage using my hands, the transistor opens, and at that point the chain can move. But if I reverse direction, the transistor closes and the chain is blocked from moving. So it acts like a diode. To change direction, we can change the lever position and it works in reverse. The electrical sockets in our homes provide alternating current, where the current reverses direction. So we have a positive and then a negative voltage. But our electronics use direct current, where the current moves in just one direction in the positive region. We need a rectifier to change from AC to DC, and that uses just 2 diodes in a basic configuration. The output is rippled, but it's only in the positive region, and so this is a rough DC output from an AC input. If we connect 2 diodes from transistors like this, we have an AC input, but we get a rough DC output at the speaker. In electronics, we can use capacitors to smooth out this ripple into a smoother DC signal. But we can do that in Spintronics too. The capacitors provide a low-pass filter, and so the rotation of the speaker is now much smoother. What circuits could you build with these components? Let me know in the video description down below. There's so many incredible circuits that we could build with these kits, and I highly recommend that you check it out. There's a link in the video description for you, along with a simulator to even test your designs out. So do check this out, links down below. Check out one of the videos on screen now to continue learning about electronics engineering, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, LinkedIn, Twitter, Instagram, TikTok, and theengineeringmindset.com.